Okay, now we continue with errors. So an error refers to the degree of lack of precision or lack of accuracy of a numerical computation. So in the previous slide, we talked about precision and accuracy, right? The lack of precision, lack of accuracy is what an error is. True error will be measured relative to the true value. So true error is the difference between the true value and your approximate value. So your approximation minus the exact value or the true value is your true error. Mathematically, we can write an expression for the true error as true value minus approximate value. And typically we work with the absolute value, right? So whichever one you put first is not important because it's whether it's negative or positive, when you take the absolute value, you will get a positive value. So absolute true error is the absolute value of the difference between the true value and the approximate value. Again, it's true error because it's relative to the true value. Relative true error will be the ratio of this guy, which is the true error, to the true value. So it's true value minus approximate value divided by what? The true value. That's why it's a relative true error. It's relative to the true value. And this will be a fraction which can be expressed in percentage. True value in many cases is unknown, especially in numerical computing. If we knew it, we wouldn't be solving for it, right? So we need to be able to quantify errors relative to another metric since we don't have the true value. So what we use is we compare the estimate at a current iteration with the estimate from the previous iteration. And like I discussed earlier in this video, as that difference becomes smaller and smaller, you are approaching the true value. So that's what we do in numerical computing. So we measure something called convergence, and we typically use a tolerance value. When the difference between the value at the current iteration and the value at the previous iteration is less than a tolerance value, which could be as small as 1e minus 5, then you're said to have converged on the value, on the solution, basically. The approximate error is the difference between the present approximate value and the previous approximation. So unlike these true values, this is relative to the previous iteration. So there's a difference between the present approximate value and the previous approximation. Very useful in numerical schemes where you never know the true value. So this is the expression for the approximate error. Current approximation minus previous approximation, which is different from this where you're using the true value relative to your current approximate value because you know the true value. Sources of errors in numerical computing. Two main sources of errors: truncation error, round-off error. And these two are conflicting errors. So in general, when truncation error becomes very small, round-off error tends to get bigger, and I will explain that shortly. So what is truncation error? It's error because you truncated, meaning you cut off some terms. If you remember Taylor series expansion for f of x for f of x plus delta x is going to be this, right? Plus delta x f prime of x plus delta x squared 2 factorial f prime prime of x, and so on. Well, in our finite differences, we typically cannot carry all these terms, right? In any numerical scheme, for that matter, you can't continue this sequence forever. So we generally truncate at some point, and that gives you truncation error. So because you can't continue this expansion infinitely. This, by the way, like I said, is a Taylor series expansion. So this will be the truncation error, the error that occurs because some of the numbers or some of the steps have been shortened or truncated, which is why it's called truncation error. And we only use a few number of steps. In general, we have more truncation error in a coarse mesh than in a fine mesh. What is a coarse mesh? If you were to simulate this domain with 9 grid blocks, right, that could be a coarse grid. Same 9 grid blocks. What if we divide each grid block into 2? Which will have more truncation error, this guy. Why? Because truncation error, as you can probably see from here, is a function of delta x. Delta x could be the size of this grid block in this direction. And so, because the error is a function of the square of the delta x, the truncation error will be a lot more in a grid block that has bigger delta x, right, than in a smaller one. So, truncation error increases as the mesh becomes more coarse. What is round-off error? What's 1 divided by 3? Is 0.33333 in infinite number of places, right? Can your computer store an infinite number of 3's? No, right? It's going to stop at some point. The fact that your computer is not able to store an infinite number of decimal places leads to round-off error, because when you stop after a certain number of decimal places, you are rounding off the number to the nearest whole number, the last digits in the decimal place. You round it up, and that creates an error, because an error is a loss of precision, right? Based on the definition of error shown on the previous slide, lack of precision or lack of accuracy. So because you're not able to carry an infinite number of decimal places, well, you introduce a round-off error in your computer. And this could be significant if you're looking at the extremely small number of, extremely fine mesh. If delta x becomes so small, it becomes very minute, and then it begins to struggle with these decimal places. Although truncation error is reduced, round-off error now increases. I hope that's clear. I can explain that one more time. We already mentioned that truncation error is larger when you have coarse mesh. So when you go to finer and finer meshes, your truncation error goes down, right? Truncation error goes down. When the truncation error keeps reducing because you're using extremely fine meshes, at some point you will be losing accuracy in the decimal places you're storing these dimensions at. And because they are so small, these round-off errors accumulate, and round-off error actually increases because your mesh is getting too fine. So many times there is a trade-off between your truncation error and round-off error. But in general, your truncation error is usually the more common one because it's already extremely computationally expensive to solve these kinds of systems with very fine meshes. So most of the time, you're working with a pretty coarse mesh because that will run faster, and then you're carrying over truncation errors.